Hi everyone, we are moving right along in chapter 2. Before we dive into today's lesson, I want to do some clarification. So the book ended up switching some of the lessons around in chapter 2 between the 4th edition and the 5th edition. So we are currently working out of the 5th edition, but some of my videos were made earlier. So here's what I want to clarify. If you go back to what I called lesson 2.1, it's actually lesson 2.2. And we are not doing lesson 2.1. That will match up with what you see on your vocabulary sheet, as well as what you see on the list of homework assignments, and as well I will refer to on the online graded homework. So today's lesson, if in your notes you will take a look, it says lesson 2.2. That is incorrect. This is lesson 2.3. All right. It might not say finding the nth term in your book, but it might say something like, I don't know, visual patterns or something. But that's what we're going to be doing. And we're not doing all of lesson 2.3. So please pay attention to what we're going to do versus, everything that the book presents. We talked yesterday about the idea, or in the last lesson, about the idea of inductive reasoning and noticing a pattern and coming up with a conjecture or a generalized rule. And that's what we're going to be focusing on today, except we're going to be looking at numeric patterns instead of visual patterns, which is what we focused on in lesson 2.2. So what I actually have for us right now is a couple different things. I have a table. So n here represents the term number. And then this value down here represents the term value. And I am actually telling you the rule. I have already done the inductive reasoning for you, but we're going to work up to this point. So again, when I have n is 1 and I substitute 1 in for n minus 5 is negative 4. When n is 2, 2 minus 5 is negative 3. When n is 3, 3 minus 5 is negative 2. And again, you can use a calculator for this. So we're going to go ahead and we're going to substitute each of these numbers in for n, and then we're going to get a value. So if we were to continue this, that's what we would get. Now, again, when we look at this, if I give this to you as just a sequence of numbers, you're just going to see these numbers down here. So it's implied that negative 4, since it's the first number listed, is what happens when n equals 1. So go ahead and do that for 2, 3, and 4. And then we're going to talk about what's happening with this idea of a difference. We're going to talk through that. So in this one, 4 times 4 is 16. 16 minus 3 is 13. 17. 21. 25. 29. When n is 4, negative 8 plus 5 is negative 3. Negative 5. Negative 7. Negative 9. Negative 11. Here, when n is 4, 3 times 4 is 12, and 12 minus 2 is 10. Then we will have 13, 16, 19, and 22. Now, maybe you were doing what I was doing. Maybe you were taking that n value, substituting it in, doing the math, and getting the answer. Or maybe you noticed something else. And this is what I want us to look at right now. Maybe you noticed a pattern here. So to go from negative 4 to negative 3, I add 1. Negative 3 plus 1 is negative 2. Negative 2 plus 1 is negative 1. Negative 1 plus 1 is 0. 0 plus 1 is 1, and so forth. We call that the difference. So the difference here means you take a larger term value, so for example, term 4, and you subtract the term before it, so term 3. So to get this difference, I could do like negative 1 minus negative 2, which is negative 1 plus 2, which is 1. I mean, it might have been easier for me to start at term 8 and do 3 minus and subtract term 7. Or another way to thinking about it, instead of doing the subtraction, is just say, okay, how do I take term 3 and then get to term 4? I add 1, so that's my difference. So I want you to do that for each of these next ones. You can pause the video to do that. For example 2, you should have noticed that the pattern is to add 4, so that's the difference. For example 3, the pattern was to subtract 2, and then for example 4, the difference was 3. And again, the pattern was to add 3. So what are you noticing every time? What is the connection between the difference and the rule? So again, this is the rule, okay? I hope you noticed that the difference was the coefficient in front of the n. Okay. And what we noticed in all of these is they had what we call a constant difference. And so because they had a constant, and actually we're going to refer to this as the first difference, that implies that all of these function rules are linear. Our book also goes through quadratic function rules, but we are not going to take a look at that in this course. So let's go ahead and go to our vocabulary sheet. Also, something I wanted to bring up is that in the lesson that I had recorded on section 2.2, I did not give you the vocabulary in the vocabulary sheet. I gave it to you within the video on the actual notes page, but I pulled it out of there. So again, if you did not record that vocabulary in this vocabulary sheet, you can look it up in the back of the book. You can rewatch that portion of the video. But I strongly encourage you to have all the vocabulary in one place, and that's why I like to put it on the vocabulary sheet. Okay, so a couple things that we had in lesson 2.2 that we want to make sure we know. So what is the idea of the nth term? And this is what we're going to be finding in a minute. But this is the idea of we are finding a rule. And when we find this rule, it's usually some sort of equation or expression. That describes a general term called n. And n again is our variable here. And so if we want n to be 7, if we want to find the 7th term, we set n equal to 7, and we say, okay, what is the value of the 7th term? But when we talk in more general ideas, when we are applying and finding a conjecture, we're talking about the nth term, which is some term that we know is in the sequence of the series, and it's described by this function rule, where we have this unknown n, but it's in there. Now, a linear function, which is what we are studying, has a function where the rule has a constant first difference which is the coefficient of n in the rule. The other things that we should have remembered about linear functions, because everybody here has been through Algebra 1, is remember linear functions make a line in the plane when graphed. And also, all variables are to the first power. And that's why we have an n to the first power. We are doing a more geometric application, and so we're not necessarily graphing these function rules in the coordinate plane, but again, we certainly could. The other neat thing, and I'll go back to our note sheet for this, is to remember that this constant first difference, which makes things linear, is referred to as the slope. It is the change in y over the change in x. Now, all of ours, our n's were going up by 1 because, again, we're generating sequences, and so we're not skipping points or skipping values. We're doing integer values. First term, second term, third term. We're not jumping from the first term to the seventh term. So that's why we didn't necessarily look at the change in x, because all of our n values were going up by 1. So that's just like a little aside in a connection. So what we're going to be looking at in this lesson is looking at a numeric pattern like we had that is going to be linear. We're going to make sure we know it's linear by identifying that constant difference, that constant first difference. And then we need to get the other part of the rule. And the other part of the rule is going to be a plus or minus something, okay? And again, if you recall from linear functions, this would be our b value, aka our y-intercept. We're not exactly looking at it like that, but that is what it is if you were to graph that in plane. We're going to try one together right now, brand new one. So again, term 1, 2, 3, 4, 5, that's my n, right? And you can see I have a generic n over here. And now let's go ahead and see, do we have a constant for its difference? Are we doing some sort of addition or subtraction that is the same from term to term, from sequential parts? So to go from 20 to 27, we add 7. 27 to 34, we add 7. 34 to 41, we add 7. 41 to 48, we add 7. And if we take a look at this, yes, that is something that we keep seeing. So we do have a constant first difference, check. We do have a linear function, check. And now we need to find the nth rule. This is the process of inductive reasoning. We're looking at specific term values and specific like patterns, and then we're going to apply it for the general nth term. So that means I'm going to have 7n plus something. And my goal right now is to find that something. What goes here? Well, to do that, I actually have to go back to one of my actual term values and term numbers. So again, 6 is where the n goes. 55 is the value. You can pick any one you want. You don't have to start with 6 and 55. It will always turn out to be the same. So what that means is we're going to take 6 and substitute it in for n. And I know I'm going to take 6 times 7, which is my constant difference, add or subtract, it could be a subtraction, something to it. And I should get the value of 55. So this is where the value goes. It goes in the equals, and this is where the n goes. So now I'm just going to do a little arithmetic. If you wanted, you could put a variable here. You could put a b, because that again is what it is if we think about it as a linear function. If we subtract 42 from both sides, our quote blank is 7. So 55 minus 42 is 7. And so our general rule is 7n plus 7. I always like to try this one more time to make sure it works. Actually, I am completely wrong here. This is why I checked it. I actually went over here and I said, okay, what is 2 times 7, or 7 times 2? And if I add 7, do I get 27? This is me in real time, everybody, modeling for you what I would suggest you do, and modeling for you my mistakes, and making sure we fix them. And this does not work out, by the way. 14 plus 7 is 21, not 27. So that means I made a mistake in my math over here. So we're going to go back and fix it. So 55 minus 42, if we do the math correctly, should actually be 13. How do we feel about that? That feels better to me. So this should be 7n plus 13. And when I substitute 13 in here instead of 7, well, look at that. 14 plus 13 is 27. And again, I could pick another term and I could just double check that, but it is going to work out. So I'm glad I could model that mistake for you. I think it's important that you see how I check my work and you see how I catch a mistake. So that is the end of the first part of this notes. And then you're going to go ahead and try those example problems on this next page. which are kind of harkening back to the